Hello, my name is Varant. I am a software engineer on the machine learning infrastructure team at Airbnb, and I'll be presenting Zipline along with Evgeny, who is also a software engineer working more broadly on data infrastructure efforts at the company. So today, I'll start by talking a little bit about the machine learning workflow and how Zipline fits into it, and then more specifically about the problems and challenges of feature engineering and how Zipline offers a solution to those specific problems. Then I'll hand it over to Evgeny, who will talk more about implementation of Zipline, kind of how we set about making it work, the results we got from it, and we'll leave some time at the end for questions from you. So the machine learning workflow in production. Usually when an ML practitioner, be it a data scientist or a software engineer, starts thinking about machine learning, they usually start with an idea. And this is something in the real world that they want to make a prediction about given incomplete information. So from the data side, the main two things that we start with is labels, which is the target. That's the thing that we're trying to predict. And then features, which is the information that we know about the world that we know to be predictive of this target. Given those two things, we can train a model that results in model weights and parameters that we can upload to the online serving environment if this model is a model that needs to take online traffic. And if so, then it also needs to get the features in the online environment. So what that means is that it actually needs the features to send to the model to then get the score and do the thing that we were setting out to solve the problem that we were setting out to solve in the first place. And the important assumption is that the features that we give the model in the production environment and the features that we use for training are the same, that they follow the same distribution. And this is a pretty big assumption, pretty critical to the success of the whole project. So Zipline comes in basically at that level. It is a system that you can use to get your feature data for training and then also get your feature data for online serving. And what the framework does is guarantees consistency across these two distributions. So machine learning workflows span a pretty broad range. And one way that we can kind of start to differentiate them is by the number of data sources involved for their prediction. So on the left side, we have very unstructured use cases that have basically one or very few data sources. So let's take image classification, right? In this case, you basically have an image and you're trying to classify it. There's very few other data sources that you're going to join in to make this prediction. But on the right side of the spectrum, you have something like fraud prediction, where you might use a whole lot of different, event sources, event streams to make this prediction, right? So instead of just a simple image, you might have like logins, failed logins, searches, payment information being updated. And all these things are basically different data streams that we're joining together. So where this leaves us is that the infrastructure challenges are very different from one end of the spectrum to the other. And in the Zipline case, we're really focused on the right end of the spectrum, where you have a lot of different data sources that you need to join together to do your machine learning project. To talk about this a bit more concretely, we can actually use an example. And we can kind of see how feature engineering has a very different definition on either end of the spectrum. So if we look at the NLP case, for example, feature engineering might mean taking this blob of text that we're trying to make some prediction about, that we're trying to extract some real world information about, and turning it into n-grams, right? This is like a transformation of your single data point. On the other end of the spectrum, though, we have personalized search, and you might want to construct a feature such as the sum of purchases in the last 7 days, right? This involves finding a whole new data stream, in this case purchases, and providing some aggregation over it. That's kind of the fundamental difference that we're talking about on either end of the spectrum. The other way that we can kind of classify and differentiate the machine learning use case space is by offline batch versus online real time. So in the offline batch workflow, such as email marketing, what you'll be doing is taking all users, for example, segmenting them into a couple of different segments, and then sending some email marketing workflow to those users, right? So in this case, the model that you're making never takes online traffic. It never serves an action from the website, from the web application itself. And as a result, you don't have features in the online environment. And as a result, you don't really have that online-offline consistency problem that I was talking about earlier. But contrast that with a case like personalized search, right? In this case, the web application is responsible for providing search results to the user. And so what we have is a need for those features to be available at search time in the environment that search is running in, aka in the online serving environment. So now we have this case where you train your model is very different from where you serve your model, and it can lead to inconsistencies across the feature distributions on both those places. And that's really one of the dangerous things that we saw happening quite often at Airbnb and was part of the motivation for Zipline. So what I'm going to talk about now is why, in those particular cases, many different data sources and online real time, like why is feature engineering so much harder in that case than it is in the case of image classification, where you're basically just turning pixels into RGB representations, or NLP, where you're n-gramming your word bag, right? So what we saw at Airbnb was that an ML practitioner, and actually we found this quote in a NIPS paper that we really liked: a mature system, a mature machine learning system might end up being at most 5% machine learning code and at least 95% glue code. We found this to be very true at Airbnb, and especially in those cases that I was talking about earlier, where you're online and you have many different data sources that you're joining together for your data pipelines. And what we found was that the reason for this 95% account being so large, that 95% was in fact mostly data management, mostly feature engineering and data pipeline management. So let's think about why this is the case. So in this case, we have a couple feature values. F1 and F2 represent features, right? So it might be the sum of searches, or as I said before, the sum of purchases in the past 7 days. Each of these feature values changes over time asynchronously and kind of independently of one another. So they have their own timelines, and they're always changing. Now, in the personalized search case, for example, the product will then demand feature values for serving as of some point in time. So if what we're trying to do is provide personalized search results to the user, for example, then this point in time here, this P1 point in time, is when you as a user perform a search, right? Now, of course, the label for our model comes in sometime in the future. In the search case, it might be, did this search convert to a purchase, right? That's a reasonable label you might apply to this model. And that happens later. So you kind of have these 3 timelines. Or rather, you have these many timelines, multiple feature timelines, prediction timeline, and then label timeline. And what you want your training set to be is the feature values as of the prediction time plus the label value that comes in later. So what is the right way to do this? What is the right way to generate this training data? The obvious solution that a lot of companies implement, and actually Airbnb as well implements this in many cases, is log-based training. So what this means is that the application that's making the prediction, in this case it might be the search application, is also responsible for logging the feature vector that it uses for that prediction to a message bus, probably Kafka or something similar, that then ends up in the data warehouse, right? So then what you have in the data warehouse is these accumulating logs that you can join with your labels that eventually land as well in the data warehouse, and those 2 things together make your training set. So this is a pretty reasonable approach, actually. It's great with some fine print. It's easy to implement. The logs can be used for auditing and debugging, and any data point that you have in production can be logged relatively easily. Also, another really important point to note here is that the consistency is guaranteed. So what we mean by that is because you're logging your data for training from your scoring environment, there's no chance of those 2 things diverging. But let's look more closely at the fine print. What's the problems here? So a couple small ones. Sharing features is hard. So if you're logging features for one model and you want to use that same definition, such as, I don't know, like a user's IP address or something in a different model, then you have to log it again. And for that other model, you can't easily define a feature once and use it multiple times. Testing new features requires production implementation. So if I want to add a new feature to my log, I have to go and ship some code to production to write that log, to log that new feature. But really the biggest things is that it slows down the iteration cycle and it limits the agility in adding new features. So let's look a little bit more closely at this and what I mean by that. So we have our F1 and our F2, and that's fine, and we logged out our prediction 1, right? But let's say now we're adding a third feature, feature 3, right? And I add that sometime in the future. Or let's say I add that today. I have all these training rows, right? Such as that one example here, but I have many of them from the past that I can't go and magically take this new log value that I started logging and apply that log value to those, or sorry, apply that new feature to those old logs, right? Those happened in the past. I can start logging today moving forward, but I can't magically make that log go back in time. So when is this a problem, right? So I mean, so then, when is this a problem? So what I can start doing is I can start logging it, and I can, accumulate more data, and gradually I can get new training data that includes this new feature value. And that's fine, because eventually I'll have enough data to retrain my model. But when is that fine? Like, when is that fine, and when is that not fine, I guess, becomes the question. And it's not fine in some cases. So let's consider Airbnb, where we're a travel business, right? And we have seasonality in our travel trends. And a lot of our models need to train on a year of data to account for that seasonality. So if I'm waiting for my logs to accumulate, then I'm basically, every time I launch a new feature, I have to wait a year to have that feature basically accumulate seasonal values. So that's not great. In other cases, labels take a really long time to mature. Let's say it takes 60 days or 90 days or something for your labels to settle before you're confident in training on them. Then once again, you're stuck waiting 60 or 90 days to go to production with a new feature. So this is really the main problem that we saw, was that we weren't able to adapt to changing user behavior. We notice user behavior changing on our platform, and we want to add some new features so that our models are more attuned to this, and we end up waiting a really long time for our logs to generate enough data. So what's ideal? Ideally, we can define a feature definition once, have that feature definition be available in the online serving environment and in the offline training environment, and that feature should be backfillable as of any point in time in the past, and that backfill should be relatively fast, so that if I, as an ML practitioner, have a new feature idea, I can define it, test it, and deploy it all relatively quickly, and be confident that this will work in production. Furthermore, what we want the system to handle is the actual glue code, right? That annoying work of hooking up all these data pipelines and making them work in production. We really want the system to also handle that so that our developers feel efficient and they feel like they're solving the problem that they want to solve and not just writing a bunch of orchestration around it. Zipline. So that's what Zipline aims to do. That's the problem that we solve. So as I said, you define your feature definition once, and it makes it available in both environments. So up top, when we say the training pipeline, what that means is basically fast backfills in your data warehouse, right? This is the data warehouse. This is where you get your data from for training. But that same feature definition can also provide you low latency serving in an online environment. So this is probably some online key value store that you use when you actually want to run your model in production and get a production score in order to do some actioning on it, whether that be fraud detection or whether that be personalized search. And the key point is that Zipline guarantees you consistency across these two things. So let's take a closer look at what a feature definition looks like to kind of explore how Zipline solves this problem. So in this case, we have a relatively simple feature. It's powered by a Hive query, which generates raw events. And the important thing to note about these raw events is that there's no group by, there's no aggregation happening in the query itself. That happens actually outside in a separate Zipline definition. And the power of this, what this means Zipline is able to do, is that it now knows basically what the primary key that we're aggregating by and what the timestamp is on every single raw event, and it knows how to pull those raw events over any time range. And so it can now actually say, for any given primary key, for any given time range, what is the exact, for example, sum of bookings in the past 7 days, right? So as opposed to a different ETL pipeline where I define this query with a group by and some date range, and it produces one value for 1 day, Zipline can now kind of produce you any value for any exact timestamp for any primary key. And it does this kind of by knowing what the raw events are and having more metadata about them, and having the feature definition be more a way to generate the feature as opposed to a declarative statement of here is the feature and here is the value as of this point in time. So that's one side of it, right? That defines a feature. But how about the training set? So now Zipline knows, right, how to generate a feature for any primary key for any point in time. But how do you actually tell it, here are my primary keys and here are my points in time for which I want these feature values? That's what the training set API is for. So the most obvious part of a training set API is a list of features that you want to train on. And in this case, we have a relatively small example. But then the second part of this training set API, which is like the kind of the less intuitive part, is the driver query. This kind of drives the part of your training set that is saying, it's defining those primary keys and timestamps, right? So another way to think about this API is you're asking Zipline, hey, for the primary keys and timestamps that come out of this query, provide me those feature values exactly correct as of those points in time. It's a little bit confusing, so I have another way of phrasing it too. But the important thing to note at this point is that the time at which we make the prediction online corresponds to this timestamp here that we ask Zipline for those point-in-time correct things for. So if we go back to the logging example that I was talking about earlier, this timestamp here would basically be that logging timestamp. The time at which the model makes that call to production scoring, that's the timestamp that we would use to ask Zipline for these feature values. And this is kind of how we achieve that time traveling. Because the feature value knows how to provide historical points in time, and all we need to do is ask Zipline for those points in time, and we get the feature values as if we had logged them at that time. Another way of doing this, of kind of illustrating the same thing, is that the user provides the left side of this table, which is like the primary keys and timestamps, and then Zipline fills in the actual aggregations. And the thing is, every single timestamp here might be different, and that's kind of what makes this a hard ETL challenge without a tool like Zipline. But with Zipline, we're actually able to achieve this time travel philosophy of feature data relatively easily. So in case you happen to miss some of that, basically a training set is a function of features, keys, and timestamps. So I'll actually now hand it over to Eugene, who's going to talk more about the implementation and kind of the details of how we make all this work.
All right. So when we started to implement Zipline, we first needed to decide what exactly are the features that we want to support. And we roughly divided all the features that are available in Airbnb into two sets. One of them is complex features. This will be a whole project of people working, coming up with a very important score of, I don't know, the authenticity of the user profile. This score is so massively useful for certain models that it has a huge weight. But then it comes with a lot of cost, actually. All these complex features, if you think of them, they are pretty opaque on the use side, right? Like you have some score and it means something, it's predictive, but what exactly it means and how it shifts, the interpretation is hard. So if anything goes wrong in production, you now have this score that's suddenly shifted in the distribution. The model underperforms. And the problem is somewhere upstream in a complex data pipeline. So what that means is that assuming certain bugs are inevitable, you will always pay some fixed capacity of your team to support these complex features. The opposite of this is very simple features, like let's count stuff and sum stuff and create Bloom filters, something very simple. And these features usually have lower weight in the model, but it's easy to generate them. They are very simple to compute, and you can actually come up with a large number of them and crowd the space sufficiently to actually capture what you're trying to predict. So what Zipline does is it intentionally makes this compromise of saying we will support the simpler features and support the data scientists to iterate on the simple feature space so quickly that they come up, say, with 100 features in the same amount of time that they will come up with one complex one. And this should support them in case of some shifting distributions or changes in production. Similarly, these simple features are much more robust. Let's say one of the pipelines goes wrong, and for some reason the sum is not as good as it used to be. But because you have 100 of them, usually the model will be sufficiently smart to compensate for a single simple feature going wrong. So more concretely, when we talk about the features we support, is sum, counts, min, max, first, last. The last n happen to be very useful for certain cases of behavioral prediction. Statistical moments like mean, skewness, and kurtosis. Approx unique count, approx percentile Bloom filters. And then we add the ability for you to define windowing on top of that. More concretely, we want the operation to support this particular set of properties. So it needs to be commutative. That is the order of the operation. Applying it to two operands, no matter in which order, gives you the same result. It must be associative. If the operation supports reversibility, then we have additional optimizations for that. So for example, plus is reversible, but max is not reversible. If somebody deleted the top review for the listing, I don't know what was the previous top review. And what's more important here is that the operation must be O1 in the computation side, but also it must be O1 in space. Because anytime you store the feature in an ever-growing representation, that means that deserialization of this feature is also ON, and then you cannot support this in streaming fashion or compute that quickly. So our serving pipeline for Zipline is essentially the classic Lambda architecture. You have a batch implemented in Spark, and then we have the streaming implemented in Flink, primarily for latency purposes. And then both of them upload the data to key value stores. And finally, the Zipline client will get the data from both sources and combine them at the time of serving. The batch part is computing values daily as of 0 UTC, and then from 0 UTC forward, you have the streaming part. And when we started to deal with the data that the users are actually want to use, you will see all sorts of crazy cases there. So if you are to implement any sort of infrastructure for data, implementing it for the nice cases is the simplest of all the problems. Usually, there will be like some feature that is like, was good today, but yesterday somebody made a change, and then now half of your page views are coming from some test client or something in this particular environment. Or like the query has changed and they accidentally selected something that they shouldn't have selected. So what that leads usually to is the data pipelines run most of the computation, and then one struggler machine is like computing for like hours and never finishes. And the obvious solution to that is provided by Spark. It's the aggregate by key feature, or like the equivalent in dataset API, which essentially allows you to combine the data locally on the executors before finally merging the data. So the data is partitioned randomly and then assigned to every executor. Every executor, as it goes through the task, it combines all the values with the same keys locally before sending it for the shuffle part. And after the shuffle part, this is where the key assignment happens, and the executors just process the data with the same key. So this essentially puts a huge denominator of the entire cluster size in front of the skewed key, which allows it to be tractable. On the training data pipeline, we have another information coming in. It's not only the feature definition and the events that you use to compute the feature, it's also the timestamps that are corresponding to the key. And what we saw in production as well is that sometimes they are trying to key it on, say, on an IP address. And the IP address is the IP of the caller. But at some point, somebody introduces like an async ready, like the rescue kind of infrastructure, where the client that calls the API actually becomes local to the machine. And it faithfully logs that the IP is actually 127.0.0.1. And then suddenly, a huge portion of your driver becomes this 127.0.0.1. So this is only one out of, say, 50 other keys, right? So it's like only one feature, only few features are affected. But this actually happens in production, and when you have a lot of keys, it's very hard always to track what happens with every single one of them, especially as you don't really control the environment that affects the keys. And in this case, like 127.0.0.1 becomes like 50% of your training set examples for certain features. And this might be like hundreds of thousands of examples for a relatively reasonable model of like XGBoost or something. And the naive solution is obviously, let's just treat this as the same thing that we did for the computation of the feature. Let's just key this with a key and timestamp, and then aggregate this independently for every key timestamp. Unfortunately, what happens is that the complexity becomes the multiplication, the product of number of timestamps by the number of events, which is untractable in many cases. And basically, it works for some training sets until somebody messes up something, and then they're coming back to you and saying, like, your code doesn't work. And when you see, it's actually this kind of type of data skews that are in the driver side now. Like, one key has too many timestamps, like hundreds of thousands of them. So let's see, why is that a problem exactly? Like, how this manifests itself. So let's consider the non-windowed case, where you don't have any windows. So if you don't have any windows, then let's say this is, for one key, you have these timestamps in the driver. They're saying, I want all the features at timestamp 1, 3, 7, 8, 10, 15, 18, 20. And then when the system sees an event at timestamp 6, it has to update the aggregates for all these timestamps that are following it, because this event needs to be accounted for in all the following aggregates. So it changes 6 out of 8 aggregates. Another event comes at timestamp 9, it changes 4 out of 8 aggregates. So you see that there is like a lot of changes that it needs to account for in this naive solution. Obviously, we can optimize that because essentially we don't need to remember all the aggregates. We don't need to change all the aggregates that are affected by the event, especially in the unwindowed case. What we need to do is basically to apply it only to the first affected one. So 6 only applies, the first affected one is at timestamp 7. So we just add it there, and then when 9 comes, we add it to the 10, and then in the end, we have a final step of computing the cumulative sum, and this produces you the same result as before. The complexity for that is just the number of events plus the number of timestamps, because in the end, you have this one final step of computing the cumulative sum. So this is pretty simple for the non-windowed case. The windowed case becomes a little bit more tricky. If your operation happens to support reversibility, you can do the same trick. You can apply it to the first affected one and then negate the same value of the event and add it to the first unaffected one. And then the cumulative sum will provide the same result. That's what we do for reversible operations. But as I said, the non-reversible operations like max, I don't know what does it mean to negate max at a certain point in time. So I cannot create the negative max 5. So in this case, we have to do something else. So let's assume that our window size is 5, and we have the event coming at 6, and then it affects these 3 timestamps. Instead of actually affecting the 3 timestamps, what we can do is we can assume that there exists a full binary tree over all the timestamps that correspond to this key. Now that we have this abstract full binary tree, we can actually find what is the top, like the highest, the most coarse-grained aggregates that cover the target interval. So in this case, the timestamps 7 and 8 correspond to index 2 and 3. And then we have this 2 and 3 node that basically you can add to and assume that it adds to both of the aggregates. In the end, you basically compute the sums or like the aggregation of values along every single tree path, and you get the same result as you would expect from the windows. And this is more from the product of the number of timestamps and number of events. We actually went to number of events by the logarithm of the number of timestamps, which is again a more tractable problem, more tractable solution. Finally, when we consider different data, when we consider all the features that Airbnb uses, there is like 3 major sources of data that we have to deal with. And the implementation of the aggregation for all of them requires certain details that we need to account for. I won't go into this too much, but like the implementation there's like a very simple case when your features are actually already pre-computed for you upstream. So there's like some pipeline that already exists. People trust it. It works perfectly for years. So why change that? Let's just let these people say, I want everything from this table and upload this to production and use this for production serving. There's the case of Jitney, which is the Airbnb event bus. So in this case, we have thousands and thousands of events logged in production. And what you want to do is, for example, the number of searches will come from a Jitney event. And then we need to support the serialization of the Jitney events into the data warehouse and processing all your queries there. But then the same query, we have to adapt it to the streaming environment where we don't have the same Parquet representation of your events. We have a thrift serialized blobs, right? So there's like a little bit of like marrying of the data warehouse formats with the online formats, which comes into play. And finally, the one that's also very commonly used, and this is a very common source of problems where people are going and calling services, and the services are implementing some logic to retrieve something from database, apply some computation, and give you a feature. Oftentimes, that's useful, but occasionally what we see is that the services will start to misbehave, and then they will return to a wrong value. Sometimes it's easier for you to go all the way to a database instead. So database is exported to data warehouse anyway. And then what we can do with Zipline is using CDC, we tap into the binlog of the database. And then now we have all the mutations coming in. So we'll have the updates, the inserts, the deletes coming in. We represent update as an insert and delete separately. And now we have the same kind of like streaming environment in which we can compute your SQL query in a streaming fashion and compute your features in real-time mode, as if you were querying the database without actually doing this. So when we integrated Zipline into our production systems, we saw a number of results coming in. So first of all, the workflow for people working on machine learning models actually improved considerably. We saw that people are doing some very small mistakes in their data pipelines and then debugging them for a very long time. Because if one of your pipelines is like, say, have a certain type of data leakage, right now in machine learning, you'll catch that all the way downstream when you push it to prod, and you'll see that it's hugely underperforms compared to what you have in a training and test environment. So what Zipline allows you to do is like catch this, iterate on this quicker by running this process multiple times ahead of time. If you see any problem in your data, you can recompute your training set in a matter of several hours, which is a huge productivity boost, especially for some models that we see like months of, it takes like a whole month to run to compute a training set. So custom aggregations, it was also a source of a lot of problems because people will start doing the custom joins of data, and then when they do custom joins, oftentimes they will get it wrong. It's all the SQL with the join looks roughly the same, but the implications of what that means actually is very different. And people will get the join wrong, or like they will get the filtering wrong, the assumption wrong, and the data will be messed up. And they will work on this, like the fact that the data is messed up doesn't prevent you from training the model. It still takes like a day to train the model, run hyperparameter optimization, like see all the results, and then figure out that it was wrong and repeat the whole process again. So having this joins and leaks kind of more controlled by Zipline prevented a lot of these issues from happening. Also, data sketches support. Again, like people are usually, for some reason, data scientists have this need. I really need the unique count of these things. They're like, I just cannot live without it. So you tell them this is a unique count, but internally you use a proxy unique count, and this improves everyone's life considerably. The other thing that we also observed is that this is the first time where you actually can measure how consistent your data is in production versus what you do train on. Because if you only have one source, the log, that's actually the source of truth, whatever that means. Like if the service misbehaves and you log the misbehaved feature, this is the only source of truth. There is nothing there is nothing else you can compare that to. But in this case, what you can do is you can start logging for auditing purposes. So you log the features that you retrieve in production, and then you run the backfill on the same timestamps, and then you compare what your backfill tells you and what the log tells you. And you can say what is the discrepancy in the distributions of features in production and in your backfill. And that allows you to better understand how your data is actually generated, how fast it changes, how fast you can actually react to that, what are the keys that are messing up the computation and stuff like this. So this is like more introspection to your data for machine learning. And the other thing is that it's mostly the speed. The speed is of iteration on the model is actually, I think, the king. If you think of it like what we really, really want in the end is for data scientists not to be able to express themselves fast enough, but we will be able to backfill the data for them with like undersampling and other stuff. But even now, what we are seeing is that a 10x improvement in the backfill allows them for the data scientists and data engineers to do way more iterations and chisel out more bugs from production ahead of time. If something goes wrong, just like delete the training data set, backfill it again. In a few hours, you have a new model. That's a huge productivity boost for people trying things. And this also encourages them to be more creative, because if you can test one thing a day, then you have like that many things you can try. If you can test one thing a week, you're a little bit slower. And once it approaches a month, likely, with a performance cycle, you'll not be training too much. So that's pretty much everything that we wanted to talk about. If you have, we have a few more minutes for questions.
Yeah, we have a few minutes left, so raise your hands, and I have the mics.
I'm sure you probably get asked this all the time. If you've done like, I don't know, 2 years on the project, not use Zipline, can you then implement Zipline afterwards?
You can. The thing is, I think the investment in machine learning infrastructure, like the machine learning infrastructure is, it's a huge undertaking. It should not be considered as like, if we do machine learning, we have to have some sort of infrastructure. Oftentimes, especially on the product side, it's much more reasonable to go without it for a while. But I think at certain point in time, when you accumulate like a few dozen models in productions, that becomes like a huge drain on your ability to execute. And this is where I think investment is reasonable. The other thing is that I think it's an investment for a larger company. You cannot do this. Like if you have 30 people, just one person working on machine learning infrastructure is not going to bring you much. You are much better off using some open source stuff.
Yeah, thanks for the talk. Considering the computation side, do features compute independently? I mean, if you are computing several features from the same table, and what happens is if those features are in different time windows or in different aggregates, is this optimized?
Yeah. So the way we define features is using feature sets, and feature sets is essentially a set of features that are computed on the same source. So in this case, if you have one table or like one stream of data, one stream of events, then you can say I want like a sum of this and a count of that. And because aggregations are composable, as long as they're computed independently, then we can do this in parallel on the same source.
The only slight caveat is that if it's the same source but aggregated by different keys, that'll actually become two feature sets. So that's the only case where that would be slightly different, but yeah.
Thanks for the talk, it was really interesting. You talked about serving predictions, generating features for serving predictions from batch and from streaming. Do you also support serving predictions from like behind a REST client or some sort of request response model, where you're just getting like the client data is not just running over a big stream of data?
So just to make sure that I understand, are you asking about like a kind of like transient information, like the client calls you with some value, say like the text?
Sure, say you're like embedding a model in a microservice or something, and you wanted to engineer features on top of the raw data that's sent in the request.
Yeah, so this is where it becomes tricky, because once you have the model that conceals from you what is the source of data inside of it, you don't know when the data is actually changing. And if you don't know when the data is changing, you don't know when the function of them is changing. So what happens in this case is that this becomes like an opaque process for you. So there is a number of ways you can go about it. So number one, in our machine learning infrastructure, we support like a composable models, where one model you just embed it inside of the other one. So this becomes like a mono model, like that you can train end to end together. This is one approach. It's more closer to what Zipline is trying to do. But there are cases where you cannot do this in any way. So for example, in certain cases, you are using external vendors, right? So like in fraud, I think it's pretty common, where you go to a vendor, and the vendor has the network effect of like consuming data from different clients. So you use this network effect to boost your models. But in this particular scenario, we treat this basically as a hidden process from which you have like some reads at certain points in time. So every time you call the model, this external model, you just log the data, and then this log becomes the source of data for you. So you will basically use the latest known score for this user before you score your model. Does it make sense?
Yeah, cheers.
Questions are here. First of all, it was a great presentation. Thank you.
Thank you.
So how do you actually generate all these mathematical aggregate functions over multiple features? So in case if I'm working on a source table where we have multiple columns and each of them is a feature, and if I'd like to generate features, for all those columns at once using all these aggregate functions, is it possible to do? And in case if I'm dealing with billions of rows, I think you said you can do the feature engineering in real time as well. How do you handle the billions of rows in real time?
All right. I'm not sure I 100% understand the question there. So regarding the computation of things in parallel, so this is limited by the feature set. Is like if number of features are computed on the same input stream, then we just use that as to aggregate on the same key, if it's in multiple tables or like multiple sources, multiple event streams, then we do compute this separately. The thing is that you can schedule many of them in Spark using multiple threads. This a little bit improves some Spark internals by essentially executing the pre-warming of the park here reading or stuff like this on the driver before it actually gets computed on the executor. But ultimately, basically, the way Spark works is that the whole thing will be computing one feature set until it's done. Unless there is no more tasks in that, and then you'll see the other feature set as like a fading, the first one and the second one takes off.
So Zipline supports only one feature at a time?
Not one feature. It's like if you have a table where you have searches, right? So one thing you can do is you can ask how many listings the user looked at before booking something. You can ask, have they made any search at all? You can ask what is the time difference between them, right? So there's like multiple things you can compute off the same row. If this is the case, you can compute them in parallel at the same time, and that's what we always do. If you have searches and bookings, these are two different streams, and so the features for them will be computed sequentially. The groups of features related to them will be computed sequentially one after the other.
And what sort of pre-processing that we need to do before we feed in the data into the Zipline?
We don't provide any pre-processing. Essentially, what we say is we take away from you the aggregation side, and we use that to optimize that for you. You provide the SQL expression, which provides us the source of the data. And the SQL expression, the expressions in the SQL is all the pre-processing you can do. So if you have some JSON, you can extract some JSON from it, right? Like if you have something you need to multiply, you can multiply it there, but there is not a whole lot that you can do there.
Cool, thank you.
All right. Thanks for the interesting talk. Let's put our hands together once again for our speakers.
Thank you. Thank you.
Please remember to rate the session, and we'll reconvene after lunch, 1 p.m.